Hello and welcome to Week 12, Part 1 of EGM310, Change Detection. In this lesson, we will learn about how we can use satellite images acquired at different times to observe and quantify changes. In the rest of the lessons this week, we'll cover applications of remote sensing to different topics, including studies of water resources, surface motion, and archaeology. Very often, we're not just interested in making a single observation from a single point in time. We want to be able to observe and quantify changes in land cover or other variables. In this image, we see a normalized difference vegetation index for the Leeward Islands. Remember that this indicates the overall health of vegetation. The higher the value, the closer it is to 1, the healthier the vegetation. The Leeward Islands are a group of islands situated where the Caribbean Sea meets the Atlantic Ocean, including the countries of Montserrat, Antigua and Barbuda, and St. Kitts and Nevis. In September 2017, a Category 5 hurricane, Hurricane Irma, swept through the Caribbean. It was the strongest hurricane recorded to ever hit the Leeward Islands, and it caused immense damage. The eye wall of the storm passed directly over the island of Barbuda. 95% of the buildings on the island were damaged or destroyed, and the island was effectively stripped of its vegetation. You can see this in the post-hurricane NDVI image. On a number of the islands, including Barbuda, the NDVI values have dropped considerably. As St. Kitts and Nevis was hit less directly by the storm, we see more or less the same picture from before to after. Our goal with change detection is to analyze changes over time. For example, we might want to study the damage caused by a hurricane, or map the growth of urban areas or other changes in land cover. We might want to understand how forest fires have changed over time, study landslides or other hazards, or any number of other applications. We also want to have some kind of quantitative analysis. For example, the percent area change of glaciers or the number of landslides. We may also want to understand the spatial distribution of these things. For example, where do we see the largest changes in urban area? We usually also want some kind of accuracy assessment so that we can understand how accurate our results are and gauge how reliable the changes that we observe are. When doing change detection, we have a number of considerations. The first is time. This can be the time period considered, the rate of change, so how much time has to pass before we can expect to see a change, or the time of year. Is there a seasonal aspect to the change that we want to see? For example, we wouldn't want to analyze vegetation changes by taking a winter image from one year and a summer image from another year. That wouldn't give us anything meaningful. We also have to consider our remote sensing data, starting with the various resolutions that we have discussed. Is the change we're trying to observe of a scale that we could actually see with our data? We wouldn't expect to see centimeter scale changes with 30-meter resolution imagery. We also have to think about the temporal resolution. For periodic changes, we have to have images that are spaced frequently enough to actually capture the change. Depending on the radiometric resolution of our data, we may not be able to distinguish subtle changes in reflectance. Finally, we also want our images to be geometrically and radiometrically corrected. If they aren't, we can't be sure whether the changes we see are real or due to differences between the images. We have a number of different techniques at our disposal. Which technique we use will depend on the changes we are trying to see and the data that we have available. We'll start with visual analysis. This can be viewing two images side by side. We often use visual analysis to help us determine which technique might be most appropriate given the change and the data available. Of course, if we're doing any kind of manual mapping or classification, we might also use this technique on its own, using the techniques of visual interpretation that we discussed last week. The next category of technique we might consider is data transformation. This might be a principal component analysis, Much like with image analysis or classification, this technique can help us reduce redundancy in the data and highlight variations or differences. Also, like with image analysis, this can be difficult to interpret. It's not always clear what the principal components relate to. We can also create normalized difference indices, either of individual bands from two different points in time, or using band ratios, normalized difference indices, or other metrics. Band algebra, such as taking a band ratio or a difference, can also be a way to enhance differences between images at two different times. We could do a classification comparison, where we classify each image individually and compare the results. This may not always be the best option, however. Classifications can be noisy, and so any differences may not reflect true changes. Change vector analysis can help us identify spectral changes based on the magnitude and direction of differences. Multitemporal classification, unlike classification comparison, seeks to classify changes. For example, a change from bare soil to crops or from forest to urban areas. Finally, with a sufficient number and density of observations, we can analyze the data as a time series. For example, we're looking here at a time series of glacier elevations. Dynamic visualization refers to somehow viewing the two images dynamically. This could be using the swipe tool in our GIS software, flickering back and forth between the images, or looking at an animation as shown here. This animation shows a large landslide that occurred on 16th February 2014 on Mount La Perouse in Alaska. Dynamic visualization can be used to select the best technique given the data and the changes. It can also be used to perform the analysis, again, using the visual interpretation techniques that we discussed last week. Another type of visual analysis could be to form multitemporal false color composites, where we composite bands from multiple dates rather than multiple bands from a single date. Areas without change should be shades of gray, black, or white, while changes should appear in color depending on how we composite the image. In this example, I've set an image from March 2nd to the red channel, and the green and blue channels are an image from February 7th. In this case, red pixels correspond to shortening shadows. This is where the March 2nd image is brighter than the February 7th image. Blue areas are the landslide, and white and gray pixels are areas without change. We can also see some areas that correspond to glacier motion. The area down in the lower left of the image, for example, shows where crevasse motion has led to a contrasting pattern of red and blue as the crevasses have moved. Much like single image analysis, we can use image algebra to enhance the differences between our two images. On the top here, we have a band ratio where I've divided the February 7th image by the March 2nd image. Pixel values close to 1 correspond to no change, while pixel values below 1 correspond to areas where the March 2nd image is brighter, and pixel values above 1 correspond to areas where the March 2nd image is darker. You can see the rock avalanche highlighted clearly as an area where the March 2nd image is darker. Below this, we have a normalized difference index where I've taken the March 2nd image minus the February 7th image and divided by the sum of the two. For this kind of change analysis, we usually have to pick a threshold value to classify where significant change has happened. We might pick a difference of about minus 0.5, 0.15 for the normalized difference image, and maybe something like 2 for the band ratio. We can also do algebra with arithmetic images. As an example, a difference of differences can show us changes in multiple bands at once. Think back to the first slide of this lesson, where a decrease in NDVI shows us where large changes in vegetation cover have occurred due to, for example, a hurricane. For a multitemporal classification, we perform the classification using stacked images. All of the bands from time 1 and all of the bands from time 2 are combined in a single image. Unlike with single image classification, the goal with multi-temporal classification is to classify change classes and non-change classes. We can illustrate this with a relatively simple example. Here we have a scatter plot for a given band with the values at time 1 plotted along the x-axis and the values at time 2 plotted along the y-axis. You can see that we have roughly 4 groups here that are clearly separated from each other. The groups that fall close to the 1-to-1 line are our non-change classes. They have roughly the same values in each image. Perhaps the low value group represents grass. This might be the reflectance in the visible red band, where grass doesn't appear as bright. We might also have snow as the high value non-change group, because snow has high reflectance in the red. Now that we have this, we can look at the group of pixels that has high reflectance values at time 1 and low reflectance values at time 2. This could represent pixels that were covered with snow that melted in between time 1 and 2, exposing the grass underneath. We also have the opposite, pixels that had low reflectance values at time 1 and high values at time 2. These would probably represent pixels that are grass that was covered with snow in between time 1 and 2. When we're doing this sort of classification, one thing we have to think about is how similar are our change classes to our non-change classes. This is going to depend on the image we have. Images with only visible bands might be difficult to distinguish given how similar many surfaces appear in visible light. It will also depend on the type of change we're trying to see as well. If the changes are subtle, it might not be easy to distinguish them reliably, just like when we're trying to classify single images. We can use principal component analysis to help with this. It will help reduce the redundancy in the image as well as the dimensionality. We might be able to use only 3 or 4 bands from each time period, rather than the full complement of 10, 11, or even more bands. We can also use principal component analysis to do change detection on its own. It helps to maximize the variation that we see, but remember that this is often difficult to interpret. If we think about band values as forming vectors in space, we can analyze the differences between them. The example here shows the red brightness plotted along the x-axis and the near-infrared brightness plotted along the y-axis. The longer vector represents the pixel values at time 1, and the shorter vector represents the pixel values at time 2. We could subtract the time 1 vector from the time 2 vector to get the change vector. In this case, the change in red brightness, or the x direction, is plus 12, and the change in the near-infrared brightness is minus 39. So perhaps this represents a change in vegetation that has become stressed due to drought. We've shown an example for just 2 bands, but we can do this for as many bands as we like. We can also calculate the angle and magnitude of the differences. This vector has an angle, minus 63.5 degrees, or about 300 degrees going anti-clockwise, and a magnitude of 40.8. The magnitude represents how much change has occurred. That is, how different the pixel is at time 2 when compared to time 1. The angle can be interpreted to determine what kind of change has occurred. We can threshold the magnitudes for significance. We don't necessarily expect small differences to represent true changes, as these can be due to many different factors, such as changes in scene brightness. We can also categorize the angles, similar to the cardinal directions on a compass. In this 2-dimensional case, we might have 4 categories or quadrants, where both components are positive, both are negative, and then the two cases where one component is positive and one is negative. And again, this example is for 2 bands, but we can do this for as many different bands as we like. The more bands that we add, the easier it can be to categorize and interpret the images. As an example, taken from an article on remotesensing.org, we have the change vector magnitude and angle for 2 different images based on the red and near-infrared bands, one from 1988 and the other from 2011. Here you can see three different examples of pixel change. The first representing no change. We had a forest pixel in 1988 and it was still forest in 2011. Because the pixel values are the same in both years, the angle and magnitude of changes is of course 0. If we have deforestation, going from forest to not forest, we might see a significant drop in near-infrared reflectance and a slight increase in red reflectance, corresponding to this red vector here. The last change, from soil to water, perhaps indicative of flooding or the filling of a reservoir due to construction of a dam, is characterized by a drop in near-infrared reflectance, but a slight negative change in red reflectance, moving in the opposite direction to the forest to no forest change. In this lesson, we have discussed how very often our goal is to analyze changes in time. This could be before and after a particular event, such as a landslide or a hurricane. It could be more generally over time, using 2 or multiple observations. Visual analysis of change is often a first step toward determining which technique might work best for detecting the kinds of changes we are interested in studying, or it could be a way to analyze change on its own. Many of the techniques we've already covered, including principal component analysis and image algebra, can be adapted to analyze temporal changes as well. They can also be combined in a way to enhance the differences between images acquired at different points in time, similar to how we analyze individual images. Finally, the choice of technique is going to depend on our particular application and goal. Some techniques are better suited to certain kinds of changes and certain kinds of available data. Once again, you can read more about the concepts we covered in this lesson in the textbooks, Chapter 7 of Lillesand, Kiefer, and Chipman, and Chapter 16 of Campbell and Wynne. I've included links to 2 different websites. The first, Earth Observatory, has a number of articles and examples showing changes on the Earth's surface as observed by Landsat. The second website will enable you to make your own GIF using Landsat images and Google Earth Engine. No coding required. Finally, there are 2 videos showing examples of performing change detection using ArcMap and Landsat images. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!